Exercise 2. Graph the solution set of the indicated system. Label any vertices with exact coordinates. Determine whether the region is concave or convex. Okay, looking over this system, looks like all linear inequalities. So we've got an intersection of 4 half planes headed our way here. Okay, to make sure or at least to have a chance of getting our graph to fit on the paper initially, we at least want to make sure the boundary lines of all of these half planes will be on the paper. So let's think about what coordinate system we should use. Here we'd have a x equal to 1 vertical line, x equal to 1 for an x-intercept. This will have an x equal to 2, a vertical line, x equal to 2 as an x-intercept. This one, okay, sloped line. Let's see, intercepts. If x is 0, y will be 3. If y is 0, x will be equal to 3. Okay, third one, as far as the boundary line, the equality case goes, the intercepts. X is 0, y will equal negative 1. Y is 0, x will equal negative 2. Okay, looks like a coordinate system with x and y axes going from negative 5 to positive 5 will work. Let's see. Okay, want to scale and label the axes. So put x on here, y on here. For scaling, 3, 3, negative 3, negative 3. Okay, let's get at a contrasting color and graph the solution set of this first inequality here, x greater or to the 1. Okay, the boundary line is x equal to 1. Vertical line. Passing through an x-intercept of 1, 0. To graph this, it's strictly greater than. So we want to make sure we use a dashed line here. Okay, I'll label the equation x equals to 1. Now, how about which side of the line to shade? In this case, it's a vertical line, so x greater than 1 corresponds to the right. And because this is a system, I just use a pencil to keep track of graphs right now, because I want to only shade the true common intersection of all 4 of these half planes. Okay, so I see that. Let's go to the second inequality here. Another contrasting color. And let's see, x less than or equal to 2. The boundary line is x equal to 2. Vertical line, x-intercept 2, 0. It needs to be a solid line in this case, because that's an or equals to situation. Alright, label its boundary line equation. And as far as the shading goes, what goes on here? Less than or equal to. Okay, we are to the left of this line. Alright, so far we've reduced our possible solution set to this rectangular band here. Let's go to our third inequality. Third contrasting color. Let's graph the boundary line. If x is 0, y is 3. If y is 0, x is 3. This is an or equals to case, so we'll use a solid line for the boundary line. The equation of this, right here, y equals 3 minus x. Okay. Now, the shading. Since this has a y equals mx plus b nature to it, we can think of the y less than 3 minus x as saying below the line. So now we are down here. Okay. So far now we've narrowed it down to this little strip in here with this cap. Alright, let's go to the next inequality. Okay, let's graph the boundary line. If x is 0, y would be negative 1. If y is 0, x would be negative 2. As far as this line goes, we need to use a dashed line because this is an or equals to. Rather, it's not an or equals to situation. It's strictly greater than. Okay. We'll label the equation here. This is 3x plus 6y equals negative 6. Now, as far as the shading goes of this, what happens? This kind of inequality, maybe we test 0, 0. If we put 0, 0 in here, we have the statement 0 greater than negative 6. Well, that is true. Okay, so we need to shade the 0, 0 side of this line up here. Now, this puts the common intersection of all 4 half planes right in this little trapezoid here, huh? Okay, so now we get ready to do our real shading of the solution set. So for instance here, and then over here, okay. Now, we have some vertices to consider here. Now, we have to be a little careful on these vertices, right? All right, I'll use it like a circle template to make clear circles here. Let's start here. Now notice this vertex is the intersection of a solid line, solid line. So here's where a solid dot, I'm going to use pretty big dots here to make this clear, is required. Solid. Okay, this vertex here, a solid line, but a dashed line. So this point of intersection is not part of the solution set. Hollow circle. Okay, this point here, dashed line, dashed line. This vertex is not actually part of the solution set. Hollow circle. Here, solid line, dashed line. Okay, since it's not part of the dashed line, it's not part of the solution set. Hollow circle. Okay, now we're responsible for getting the coordinates on all of these vertices. Let's start here with this one. Okay, here's the intersection of the red line and the green line. So we can do our scratch work right maybe nearby. X equals 2 together with the green line. Y equals 3 minus x. Okay, x is simply known to be 2. We substitute the 2 for x into the second equation. Y equals 3 minus 2 equals 1. Okay, so now we have the point 2, 1 right there. Let's go to this vertex here. Now, x is 1, and the green line has its equation, so we have x equals 1, green line, y equals 3 minus x. We can substitute y equals 3 minus 1 equals 2. So right here, This point is 1, 2. And it also looks like the point 1, 2 graphically. Good. Let's go down here to this one. Here at the intersection of this blue line, x equals 1, and the purple line, which is the 3x plus 6y equals negative 6 line to consider. Alright, x is 1, so this gives us 6y equals negative 6 minus 3 times 1. Let's see, that would be negative 6 minus 3, negative 9. So y ends up being negative 9 over 6, better known as negative 3 halves. Does that look graphically consistent? 1 and negative 3 halves? Yeah, it looks pretty good. Okay, let's label it. 1, negative 3 halves. Okay, right here. What about this? This point? It's the intersection of the red line and the purple line. So now we are considering a combination of x equals 2 and the purple line 3x plus 6y equals negative 6. Okay, we can substitute x equals 2 in here. We'd have 6y equals negative 6 minus 3 times 2. Okay, that looks like negative 6 minus 6, negative 12. Y will then equal negative 2. Okay, let's see if that looks graphically correct. Negative 2 for y? Yeah, looks good. And 2 for x? Yes, looks good. Okay, 2, negative 2. Okay, got that. Let's also, for the sake of clarity, really make sure we label our solution set. So an arrow right here, solution set. Right there. Now, could have made a mistake here. Would like to give this some sort of a check to be sure. Okay. How can we check this? Well, we could select some point that is clearly in the shaded region. Let's see here. How about we go up? Let's see. All right, 1, 2. All right, 3 halves, and maybe come up 1. That's surely in the region. So the point 3 halves, 1, is a solution, or at least we are claiming so by our graph here. And so let's try substituting into each inequality. Now, since we have a point which is a solution, it must, by definition of solution, make each inequality a true statement following substitution. Okay, let's see what happens. The first inequality, x greater than 1 becomes, x is 3 halves now, 3 halves greater than 1. True. Okay, our second inequality, x 3 halves less than or equal to 2. Okay, true. Our third inequality, y, that's 1, less than or equal to 3 minus x is 3 halves. 3 minus 3 halves is 3 halves, 1.5. 1 less than or equal to 1.5. True. Okay, third inequality. 3x, 3 times 3 halves, plus 6y, 6 by 1, is that greater than negative 6? Okay, well here would be 9 halves. Okay, 4.5 plus 6, 10.5. 10.5 greater than negative 6? Surely true. Okay, looks like it did indeed create a true statement upon substitution into each inequality, so that gives us some confidence that this is looking pretty good. One more thing, look over those boundary lines, make sure we got the dashed, solid, solid, and dashed. Okay, that looks pretty good. Now, the very last item here, is this region concave or convex? Okay, Just imagine selecting any 2 points in this region, and then the line segment that connects those 2 points must lie in this region as well. Okay, that's all it takes to determine this is indeed then a convex region. Okay, that completes exercise 2. Exercise 4. Graph the solution set of the indicated system. Properly graph and label any vertices with exact coordinates. Determine whether the region is concave or convex. Okay, looking at this system here. Linear inequality, linear inequality. Alright, so we already can anticipate we're supposed to be getting a convex region that's going to have linear boundaries. Alright, so let's at least prepare a coordinate system that will fit some boundary lines. When this is an equality, that's the boundary line equation. If y is 0, x is 3. If x is 0, y is negative 2. For the boundary equation here, if y is 0, x will be negative 3. If x is 0, y is negative 5. Alright, apparently a fairly small coordinate system, negative 5 to positive 5 for both axes, may work for us. It's hard to tell with a system of inequalities what's going to happen to the final region, but at least we can get these boundary lines to appear. Label the axes. We'll scale them. 1, 2, 3. 1, 2, 3. 1, 2, negative 3. 1, 2, negative 3. Okay, get a contrasting color to sketch up the solutions to this first inequality. Again, for that boundary line, when x is 0, or rather when y is 0, x it will be 3. X is 0, y would equal 2, negative 2. Okay, for the boundary line itself, since this is greater than, we need to use a dashed line here. Can label it with its equation. This is 2x minus 3y equaling 6. Which side of the line gets the shading? Okay, let's substitute 0, 0 in here for a moment. 0 greater than 6? Oh, that would be false. So apparently it's the other side of the line, not 0, 0's side of the line. Here, this is where the shading goes. And I don't really shade this with anything dark or anything because we're just in an intermediate stage of the problem. We want the intersection of all of the individual half planes here. Okay, contrasting color. And off to this inequality, as far as this boundary line goes, as this is considered an equality for a moment, if y is 0, x will be negative 3. X is 0, y will be negative 5. Okay, now in this boundary line's case, this will need to be solid because the inequality that we're graphing right now is or equals to. So these equalities are also part of the inequality solution set. Okay, we can label its equation here. This is 5x plus 3y equaling negative 15. As far as which side of the line to shade, we could test 0, 0 here. 0 on this side, greater or equal to negative 15. That's true. Think of that number line sometimes when you've got negative numbers running through your inequality. Don't get confused. Alright, so 0 is greater than negative 15. So it's a 0, 0 side of the line that gets the shading. That's here. Alright, here's our two half planes. The intersection of them both looks to be over in here. Okay. So here. There. Okay. So I like to label this here. So we have the solution set. Now, let's see, what else have we got? Those, well, there's one vertex here. Okay, now to properly graph it, what do we need to do for that? Notice it's the intersection of a dashed line and a solid line. So this point, since it doesn't satisfy this line here, does not belong in the solution set. We need a hollow circle to go here. Okay. Perhaps like so. Okay, and we will need to get its coordinates labeled here. At this point, it seems we need to solve the system of equations, this boundary line, red, and this boundary line in the blue. So we need to take a look at 5x plus 3y equals negative 15. And here's 2x minus 3y equaling 6. This system is immediately ready for some elimination. Basically add the equations together. Here's 7x. The y's add to 0. And 15 and negative 6, that's negative 9. So then that gives us x equals to negative 9/7. Alright, I'd like to check for graphic consistency right at this point to make sure we haven't got problems. Negative 9, that's between negative 1 and negative 2. Here, negative 1, negative 2. Looks pretty good. Okay, keep going. We could use maybe this second equation as a source for y. Subtract 2x from both sides. Negative 3y would equal 6 minus 2 times negative 9/7. Okay, let's see if we go into the world of sevenths here. This will be 42/7. Minus a negative is plus. 2 by 9, 18 of them. Okay, so now we have here, let's see, 50/67. Now if we divide both sides by negative 3, y ends up becoming negative 20/7. Now that'd be close to negative 3. How about that graphically? Yeah, it looks pretty good. Okay, we go ahead and label this point here. Negative 9/7, negative 20/7. Okay. Well, that's the only vertex we had to concern ourselves with. What else can we do here? Well, let's do a little check on this solution region. Alright, so we can select something that's clearly in this region. Let's see, how about here? Negative 2, are there 2, negative 2? That's surely in the shaded region. Okay, so this means it's a solution, and so substituting into each inequality. Alright, we need to get true statements each time. Let's see what happens. First inequality. 2 times x. X is 2 minus 3 times y is negative 2. How about that being greater than 6? 4 minus a negative, let's add 6. This is 10. 10 greater than 6? True. Okay, second inequality. 5 by the x, which is 2, plus 3 times the y, which is negative 2, greater than or equal to negative 15. 10, subtract 6, we're at 9. How about 9 being greater than or equal to negative 15? True. Okay. Looks like this solution set passes at least some sort of a check. Now, the last remaining part of this question is this region. Is it convex or concave? Okay, well, imagine taking any 2 points in this region, connect them with a straight line segment. That line segment would have to also be within the region. Okay, so we have the idea that this region is convex. Okay, that completes the question. Exercise 6. Graph the solution set of the indicated system. Properly graph and label any vertices with exact coordinates. Determine whether the region is concave or convex. Alright, looking at this system, we see a linear inequality, linear inequality, linear inequality. Okay, so right away, by now we are expecting to see a convex region which has all linear boundaries. Okay, now we'd like to fit the boundaries on the coordinate system, so let's think about at least that much. We might not get the region on the paper, and we have to do a second graph, but at least we try to get the boundaries. So imagine this first one, it's an equality for the purpose of boundary considerations. If x is 0, y is 10. If y is 0, x is negative 5. The boundary line for the second one, which will be the equality version of this. If x is 0, y is 7. If y is 0, x is 2. Third one, as an equality goes for its boundary line, when x is 0, when y is 0, x is 4. When x is 0, y is 3. Alright, the first situation for the y at 10 poses a little bit of a challenge, but there were all positive y-intercepts here, so I think if we go with a lot of positive y-axis, we might be able to get this to go with a scale of 1 centimeter equals 1 unit. Alright, let's try it. Okay, labeling the axes, x here, y here. Some scaling, alright, going 1 unit per tick mark, so 3, 4, 5, 6, 9, okay, negative 3. Alright, now let's take on this first inequality here. For the boundary line, again, it was letting x be 0, y is 10. Letting y be 0, x is negative 5. Okay, now we go to sketch this boundary line, and we should be sketching a solid line because this inequality is or equals to. So at least for this inequality, the equals cases are part of the solution. Okay. We can label this line with its equation. Y minus 2x equals 10. Alright. Now, as far as the inequality goes, half plane, which side of the line gets the shading. Alright, we could test 0, 0 here. We substitute 0, 0 in here. We'd have 0 less than or equal to 10, which is true. So that means it's the 0, 0 side of the line that gets the shading. And for these, the individual inequalities, I don't shade very darkly. I just shade enough to keep track of which side is being shaded, because the goal is to get the solution set of the system, not just one inequality. Okay, so we have that. Now, let's get another contrasting color out and go to the second inequality, graphing its boundary line. Alright, now when y is 0, x is 2. When x is 0, y is 7. Okay. Now this boundary line, due to the or equals to in the inequality, needs to be a solid line. Okay, its equation, could put it here. This is 7x plus 2y equaling 14. Alright. Now, which side of the line is shaded here? Could test 0, 0. That makes this side 0 greater than or equal to 14. That's false. So it's not 0, 0 side of the line. It's this other side of the line that gets the shading for this one. Okay. So far, the solution set is out here. We have a third inequality to further intersect things here. Getting another contrasting color. Let's graph the boundary line. We let y be 0, x is 4. We let x be 0, y would be equal to 3. Okay. As far as this boundary line goes, this one needs to be a dashed line because the inequality is strictly greater than. Okay. This boundary line has the equation 3x plus 4y equal to 12. Okay. Which side of the line gets the shading here? We could test 0, 0. That would be 0 greater than 12. Well, that's false. So it's the other side of the line that gets the shading for this one. Okay, now, what is common to all three? It is everything basically to the right of all the lines is sort of the idea here. That's where the solution set appears to be. Okay, let's get going on the shading of that. Okay, so firstly in here, then here, then here, okay, I like to clearly label the solution set. Alrighty. Now, let's see. We've got the solution set. It's self-graphed, but there's some details we need to get to now. Those vertices, what about them? Okay. We see there's a couple of them. We need to graph them and label them properly. Okay. So, I like to use a circle template for really careful graphing. This vertex here, how should we graph this? Solid line and solid line are intersecting. This vertex belongs in the solution set. We would indicate that with a solid dot. So I think I'll use this one here and create a solid dot there. Alright, this vertex here. Now there's a solid line here, but a dashed line here. Now remember, solutions have to satisfy each inequality. So this vertex here does not satisfy the boundary line that's dashed, so we need to put a hollow circle right here for this vertex. Okay, see the difference? Point belongs in the solution set. This point does not actually belong in the solution set. Now, we also need to provide exact coordinates here. So let's see. Let's go here. This is the intersection of this green line and this red line. Okay, it looks like it's going to be a bit of a little systems of equations to solve to get this vertex calculated. So let's take the green line. That's the 3x plus 4y equals 12. Intersecting it with the red line, which is 7x plus 2y. 7x plus 2y equaling 14. Okay. As this system goes, some elimination. We can get these y's to be eliminated. First equation, minus 2 of the second. Okay. 3x minus 2 of these, that's minus 14, minus 11x. 4y minus 2 times 2y, 0y's. 12 minus 2 times 14, that's 12 minus 28, negative 16. Okay, now solving for x. X equals 16 over 11. Okay, is this consistent with the graph? Let's have a look. Here the x looks like it's about 1 3/4 or so. And at 1 16/11 we have got something 1 5/11. Okay, you know what? That's reasonably close to that for graphic purposes. Okay, looks pretty good. Let's keep going. Now the y-coordinate, we could use this. Oh, let's see. Maybe we use this first equation as the source. So we could sort of get started on solving for y. We'd have 4y equal to 12 minus 3x. Now x is 16/11. So let's see, what's this become? This would become, we're going to need to go to 11ths here. So 12 by 11. Let's see, 11 by 11 is 121. 12 of them. One more. 131, 132. Minus 3 by 16, that's 48 over 11. Okay, let's see, that would be 132, 48. 2 from 12 is 4. 84. Okay, 84 over 11. That's for 4y. So y is going to be a fourth of that. 21 over 11. Alright, let's see if we like that as far as graphic consistency. 21 over 11. It's almost 22 over 11. This is really close to 2. The y-coordinate here is close to 2. Okay, this is actually looking pretty good. So now we can label the coordinates here. This is 16/11, 21/11. Okay, now let's get this vertex here calculated. We need the red line and blue line to intersect. The red line, 7x plus 2y equaling 14. the blue line, y minus 2x equals 10. Alright, let's see. The y's could be eliminated here pretty easy. We could go first equation minus 2 times the second. Okay, ready? 7x minus 2 times negative 2x. That's plus 4x. 11x. 2y's minus 2y's. The y's zero out. 14 minus 2 times 10. 14 minus 20. That's negative 6. Okay, so now x is equal to negative 6/11. Does that look consistent graphically? Y and x being about negative a half or so. Yeah, okay, we're looking good. Up here, this x does look like that. Let's get the corresponding y. Suppose the second equation is a good source. Y would equal 10 plus 2 times the x, negative 6/11. Okay, so we need to be in the world of 11ths. That's going to be 10 by 11, 110, and then minus 12/11. That's 98/11. That would be very close to 9 graphically. Yeah, it is close to 9. This looks good. Okay, ready to record. This is negative 6/11, 98/11. There's the other vertex. Okay, let's be extra sure that this is correct, because when you start doing all this, it's really easy to make a mistake here. And it's not a bulletproof check, but at least it's something that can uncover shading the wrong side of the line, which is a common error, or completely misgraphing a boundary line. And for example, we might come in here and take a point clearly in our solution region. Let's see, maybe, okay, 3, 2, no doubt about it, it's in the solution set, right? Okay, so for our check, we have that 3, 2 is in the shaded region. And that means that 3, 2 is a solution. So that means we should be able to now substitute this into each inequality. So then, substituting into each inequality, let's see what we get, because we need to get true every single case, otherwise we've got an error or an inconsistency. Okay, first inequality, here it is. We now have 2 for y and 3 for x, so this becomes 2 minus 2 times 3 less than or equal to 10. That would be 2 minus 6, negative 4 less than 10. True. Okay, second inequality. Here, 7x, 7 by 3 plus 2 times y is 2, greater than or equal to 14. 21 plus 4, 25. 25 greater or equal to 14. True. Okay, one more. Third one. 3x plus 4y becomes 3 by 3 plus 4 times 2. How about that being greater than 12? 9 and 8. 17. 17 greater than 12. True. Okay. That looks pretty good. So this solution set's looking pretty nice. Last remaining question part here is determining whether this region is concave or convex. Okay, just imagine picking any two particular points in the shaded region. The line segment connecting those 2 points must also lie in this region. So, accordingly, we claim that this region is convex. Okay. Exercise 8. What geometric property is possessed by any region which is the solution set for a system of two-variable linear inequalities? Okay, if you've been kind of noticing the pattern developing, every time we answer that question, is the region convex or concave, you may have noticed that the answer we've had so far has always been convex. It's no accident. Anytime you intersect some half planes, no matter how many half planes you're intersecting, you always end up with a convex region. Okay, so here we are. The region is convex. Again, basically meaning that if any two points are in the region, so is the straight line segment connecting the 2 points. Okay.